IH bar d psi dt equal E psi. Psi, where E hat is equal to p squared over 2m, the operator. That is the Schrödinger equation, the free particle Schrödinger equation. You should realize it's the same thing as this, because P is h bar over I dx. And now, Schrödinger did the kind of obvious thing to do. Said, well, suppose I have a particle moving in a potential V of x. Then the total energy is kinetic energy plus potential energy. So how about if we think of the total energy operator, and here's a guess. We'll put just p squared over 2m, what we had before, that's the kinetic energy of the particle, but now add plus v of x and t, the potential. That is reasonable from your classical intuition. The total energy is the sum of them. But it's going to change the Schrödinger equation quite substantially. Now, most people, instead of calling this the energy operator, which is a good name, have decided to call this the Hamiltonian. So that's the most popular name for this thing. This is called the Hamiltonian. And in classical mechanics, the Hamiltonian represents the energy expressed in terms of position and momenta. That's what the Hamiltonian is, and that's roughly what we have here. The energy is expressed in terms of momenta and position. And we're going to soon be getting to the position operator there. So this is going to be the Hamiltonian, and we'll put the hat as well. So Schrödinger's inspiration is to say, well, this is going to be h hat, and I'm going to say that I h bar d psi dt is equal to h hat psi, or equivalently I h bar dt of psi x and t is equal to minus h squared over 2m d second dx x squared, that's the p squared over 2m, plus v of x and t multiplying psi. This is it. This is the Schrödinger full Schrödinger equation. So it's a very simple departure. You see, when you discover the Schrödinger equation for a free particle, adding the energy was not that difficult. Adding the potential energy was okay. We just have to interpret this, and maybe it sounds to you a little surprising that you multiply this by psi, but that's the only way it could be to be a linear equation. It cannot be that psi is acted by this derivative, but then you add v. It would not be a linear equation. And we've realized that the structure of the Schrödinger equation is d psi dt is equal to an energy operator times psi. The whole game of quantum mechanics is inventing energy operators and then solving these equations and see what they are. So in particular, you could invent a potential and find equations. And you see, it looks funny. You've made a very simple generalization. Now you have an equation. And now you can put the potential for the hydrogen atom and calculate and see if it works. And it does. So it's rather unbelievable how very simple generalizations suddenly produce an equation that has the full spectrum of the hydrogen atom. It has square wells, barrier penetration, everything. All kinds of dynamics is in that equation. So we're going to say a few more things about this equation now. And I want you to understand that V at this moment can be thought as an operator. This is an operator, acts on a wave function to give you a function. This is a simpler operator. It's a function of x and t, and multiplied by a function of x and t gives you a function of x and t. So it is an operator. Multiplying by a given function is an operator. It changes all the functions. But it's a very simple one. And that's okay. But v of x and t should be thought as an operator. So, in fact, numbers can be an operator. Multiplication by a number is an operator. It acts on every function and multiplies it by a number. So it's also an operator. But X has showed up. So it's a good time to try to figure out what IH bar d psi dt equal E psi, where E